Chapter 1.4, quick review, page 124. This is problems 1 through 10. And this section 1.4 has to do with compositions of functions. And so this is an exercise that works on domain of certain functions. And we're going to go over the odd number problems here. Exercise 1 through 10, find the domain of the function and express it in interval notation. And so what we look for when we look for a domain of a function, we look for exclusions. What is excluded from the domain of the function, and that's going to determine what the domain is, because normally unrestricted, the domain of a function is going to be all real numbers, which in interval notation is going to be greater than negative infinity, less than infinity. And so the numerator, we have this x minus 2, which is a polynomial function, and there is no exclusion based on what's in the numerator here. However, in the denominator, usually if there's a variable, or often if there's a variable in the denominator, here we know we cannot, what in math or in algebra? We cannot divide by 0. So to find our exclusion, we know that this denominator, x plus 3, cannot be what? Cannot be 0. So if we solve for x, we subtract 3 from both sides of the inequality, x cannot be negative 3. So negative 3 is the only value in this function for which that function is undefined. So our critical number becomes, on a number line, negative 3. And on that number line, we represent that exclusion by an open point. And we know that values on either side of that value of negative 3, to the right toward negative infinity, and to the left here toward the right toward infinity, to the left toward negative infinity. And in interval notation, we write this as our domain being greater than negative infinity, and then all the way up to this value of negative 3, close parentheses, a U for union. Then we pick up greater than negative 3 all the way up to less than infinity. So that's going to be our domain of this function based on this exclusion. So it's like a rope that is cut, a long rope that's cut in one place at exactly negative 3. We'll go on to our next odd number problem, which is 3. F of t equals the square root of quantity 5 minus t. And what do we know? Well, we know that we cannot what? Take the square root of what? Of a negative number. And accordingly, this value, what do we know about 5 minus t? Since we can't take the square root of a negative number, we know that 5 minus t, how do we write this? Is not negative? Well, greater than or equal to 0. You see, greater than or equal to 0 is the set of numbers that is not negative. And so if we solve for t, we can subtract 5 from both sides of the inequality. So we have negative t is greater than or equal to negative 5. Well, to solve for t, we have negative t. If we multiply this entire inequality by negative 1, we get t is greater than or equal to negative 5 equals 5. Is this correct? No, it's not. What's wrong with it? We need to switch the direction of the inequality. So instead of t is greater than or equal to 5, we have t is less than or equal to 5. And t is less than or equal to 5. Again, 5 is our critical number where we evaluate. And so we have a point at 5 and we have less than 5. Okay, so that's our number line notation. And finally, our interval notation is domain. We have greater than negative infinity starting at the lowest and going up to 5. And is 5 included in the domain? Yes. And so instead of parentheses, we use a bracket. If you happen to use a graphing calculator in this, you would see this kind of function. You would see at 1, 2, 3, 4, 5. You would see the square root function starting at 5 going back this way. Something like that. Okay. Next on the problem, which is 5. We have f of x equals the square root of the logarithmic function. This is what we call a composition of functions, a function inside of a function. So let's go ahead and take a look at this. I'm going to graph the function, the parent function we talked about in the section on parent functions. F of x equals ln x. And this is kind of what it looks like. Okay, we'll say f of x equals the natural logarithm of x, which is log base e of x. That's what it means. And so what we're doing is we're taking the square root of this function. So what do we know about the square root? We look back at problem 3, where we say cannot take the square root of a negative number. Remember that back from problem 3? We go to problem 5. Well, our output values, this function of the natural logarithm function is negative between, I'm just going to write here, negative between 0 and 1, right? Because all this here is negative between 0 and 1. What that means for us is that the function, this composition of functions does not exist until x is 1. Because if we draw a table of this function right here, okay, what do we see? We're going to put x in f of x, just to draw a few points. Well, if we put in 0, well, we know that ln of the logarithm of 0 does not exist anyway, so that does not exist. If we put in 1/2, okay, at x equals 1/2, the output value is negative, and we take the square root of a negative number, so at 1/2 the function does not exist. What's the first point the function will exist at? Well, 1. If we input 1, the logarithm of 1, so that's e to what power? Equals 1. Well, that's e to the 0 power. So we have 0, and the square root of 0 is 0. And then if we plug in a next higher number 2, well, we're going to get the logarithm of 2, the square root of the logarithm of natural logarithm of 2, which is a square root of positive number. And so our first value is, let's go ahead and write this, our domain and interval notation. We start at 0. Okay, we put an opening bracket because 1 is our first value, and we can continue up to higher numbers. This 2, 3, 4, so on. Go up toward infinity. So this will be our domain of this particular composition of functions. And if we graph this function, this one right here, I'm going to draw this down below the graph. at 1, we can see the function starts. It will be kind of like a flattened square root function, like this that I've drawn in red. So that's going to be f of x equals the square root of ln x. That's what that's going to look like. Next on our problem, which is 7, we have f of t equals t plus 5 over t squared plus 1. And so we look for, again, look for exclusions. And based on this numerator of t plus 5, no exclusions. But in the denominator, we have a variable, and we know that, again, like we did in earlier problem, I think it was 3, problem 1, t squared plus 1, we know that cannot equal 0. So if we solve for t, we subtract 1, we have t squared cannot equal negative 1. If we take the square root of both sides of the inequality, we have t cannot equal plus or minus square root of negative 1. Well, square root of negative 1 is an imaginary number, so this is not a real number solution. So there is no real number solution, and that means that there is no exclusion based on the denominator or the numerator. Now, just common sense wise, is there any number that t can be that will make t squared be a negative number? No, it's always going to, if t is 0, that's the lowest you can go. Then you'd have 0 plus 1, no exclusion. If t was negative something, well, whatever's negative becomes positive. And so what is going to be our domain of this thing? Well, it's going to be, write this in blue, domain's going to be, with no exclusion, all real numbers, greater than negative infinity, less than infinity. Problem number 9. We have f of t equals 1 over the square root of 1 minus x squared. Should be probably f of x. But anyway, notation aside, we know that you cannot divide by 0, right? So we have this thing right here, 1 minus x squared cannot equal 0. And so this is due to this, to dividing by 0. And then because we're in the radical, we also know that 1 minus x squared has to be a non-negative number, so 1 minus x squared has to be greater than or equal to 0. Well, we know that since 1 minus x squared cannot equal 0, and we have this 1 minus x squared is greater than or equal to 0, this condition here, we apply it over to the right inequality, and so we erase that little greater than or equal to, and this changes into 1 minus x squared is greater than 0. And so that's how we figure that out. In subtracting 1, we have negative x squared is greater than negative 1. And multiplying this whole inequality by negative 1, we have x squared. We have to change the direction of the inequality, so x squared is greater than 1. And taking the square root of both sides of this inequality, that's the square root, we have x is less than plus or minus 1. Well, what that means is this, because the plus or minus, this means that x is less than 1, and with the minus, this thing also means that x is greater than negative 1. Okay, that's what this minus sign does here too. X is less than negative 1, and so we flip the sign, as that's what it looks like. So on number line, the thing looks like this. Our critical numbers are negative 1 and 1, and we have a open point at negative 1, open point at 1 because those values are not included, and in between those 2 points, that would include the domain. So we have the domain interval notation. We have greater than -1 and less than 1. We could graph this function and maybe see something too. Anyway, those are all the odd number problems. I hope this has been helpful to you. Good luck with even number problems, and thank you for viewing.